Now let's talk about concavity. A curve is concave upwards on an interval when all of its tangents in the line are below the curve, as we can see here, where here would be my tangent lines. And we can see that it is curving upwards like a smile. This occurs when the second derivative is greater than 0. So the first derivative tells us the slope. The second derivative tells us our concavity. At the same rate, it's going to be concave downwards when the tangent lines are above the curve, or it is bending downwards, making a frowning face. This occurs when my second derivative is less than 0. A point of inflection is a point where the concavity changes from upwards to downwards or from downwards to upwards. So if we look at what we have here, then we start off with it curving up or being concave up from the starting point up until we hit point P. Then it is concave up again from Q to S, and it's concave up again from S to R. Between P and Q, it is concave down, and after R, it is concave down again. I know it mostly looks straight, but it is definitely concave down in this section. So, when it says, what are the intervals where the graph is concave up? Well, it's concave up from -4, the start here, until point P, 1, or from 3 to 6, from Q to S, or from 6 to 8. Now, be careful, we don't include the point S as being concave up because it's not, right? That's just going to be a cusp there. When is it concave down? Well, it's concave down from P to Q, 1 to 3, and then from R, and it just seems to continue on. So from 8 to positive infinity. Now, if we think of the requirements for points of inflection go from concave up to concave down, or from concave down to concave up. So, where did we switch from up to down or from down to up? Well, it happened at P, it happened at Q, and it happened at R. 3 of my 4 points here. Now, point S went from concave up to concave up again, so that is not a point of inflection. So the points of inflection are when X is equal to 1, 3, or 8, or at the points P, Q, and R. Note, the first derivative represents the slope of the tangent at any point in the curve. The second derivative represents the rate of change of the slopes of the tangent lines. Thus, the curve is concave up if the second derivative is positive, and the curve is concave down if the second derivative is negative. The sign of the second derivative changes at the point of inflection. So when f double prime of A is equal to 0, or f double prime of A does not exist, where A is a point of inflection. It is important to note that f double prime of A is necessary, but not enough to prove that it is a point of inflection. So if we take this example, f of x is equal to x to the 4, which means that f prime of x would be 4x cubed, which means that f double prime of x would be 12x squared. Now, when f double prime of x is equal to 0, 12x squared is equal to 0, which would occur when x is equal to 0. But when I check those intervals, from negative infinity to 0, and from 0 to positive infinity, we know that 12x squared is going to go from positive to positive, which means that the second derivative is going to go from positive to positive, which means that the graph is going to go from concave up to concave up, which, like with our example up here at point S, if it's going from concave up to concave up, it is not a point of inflection. So at any point of inflection, the tangent lines actually pass through the curve as we see here. When we go from concave down to concave up, if we solved our slope is going to cut through there and go from a tangent line above to a tangent line below, or vice versa. The critical numbers of the first derivative give us a local maximum and local minimum values for the curve. Similarly, the significant numbers of the second derivative give us the points of inflection. There are 4 cases to consider for a point of inflection, where if we take a look at our graphs, we should be able to see approximately where it's shifting from concave up to concave down to concave up. So for case 1, we have a point around here, we're going to call point A, where we can see that it goes from concave up to concave down. In the second example, point A is approximately here, where in this case we're going from concave down to concave up. In case 3, we have the change approximately here, where we're going from concave down to concave up again. And in case 4 is going to exist approximately here, where we are going from concave up to concave down. Now, at this point of A, for case 1, we can see that our original graph is below the x-axis, so it's negative. Our slope at this point of A is positive. And because there's this change in concavity that's happening here, our second derivative is going to be 0. This is called a point of increase, where that change in concavity is occurring when I have a positive slope. For the second example, our function is positive or above the x-axis. Our first derivative is negative because I have a downward slope. And our second derivative is once again going to be 0. This is a point of decrease because this point of inflection is occurring when my slope is negative. For case 3, my function is positive. My slope, well, it's occurring on the horizontal there, so my slope is 0. And my second derivative is going to be 0. So because it is neither increasing or decreasing at this point of inflection, this point of inflection is just a horizontal inflection that's taking place here. And for the last case, once again, my function is positive, but because it's occurring on a vertical line here, my slope would be undefined. And remembering that every time that we take a derivative, the domain has to be a subset of the original function. When I take the derivative of f prime of a, then that means that the second derivative would also have to be undefined at that point. So if I have a point of inflection where my first derivative is undefined, then it's going to be on a vertical inflection. Notice that every point of inflection is either going to occur when the second derivative is equal to 0 or the second derivative does not exist or is undefined. To classify the type of point of inflection, you must consider the sign of the first derivative. What is happening with the first derivative to define and classify that point of inflection?